Hi, today we'll be talking about electron cloud geometries. Just to review a little bit. When we first started this lesson on electronic structure, this unit rather, we said that the electrons are found somewhere outside of the nucleus. The next day we got a little bit better in terms of describing where they're located, not just anywhere outside the nucleus, but in these things called energy levels. So again, remember that an energy level refers to some distance from the nucleus. The higher the energy level, the further that electron is from the nucleus. Then the following day we said within each energy level, electrons are found in these things called sublevels. We have different types of sublevels depending on the shapes. And so we're going to take it one step further today. Within each sublevel, we have these things called orbitals. So an orbital represents the three-dimensional figure of the volume where there's a 90% chance of finding an electron. Essentially what an orbital is the space outside of the nucleus where you are likely to find an electron. And so the electrons are moving around outside of the nucleus, and their path traces out a particular shape. So what type of orbital the electron is in depends on the shape of the orbital in which that electron is located in, or the shape of that particular space. So shape of the orbital depends on which sublevel the electron is located in. Number 3 is very, very, very important. Any one orbital can hold a maximum of just 2 electrons. And that'll be important as we draw or write what are called orbital diagrams. So let's go over the different types of orbitals along with their shapes. We have s orbitals. So the s sublevel consists of an s orbital. Now, if you were to take a sphere and rotate it in space, how many different orientations of that sphere would you get? You would get one orientation. And so what's important here is to know this. In any s sublevel, there is only one s orbital. Now, what's different about the different s orbitals is the diameter of them. So the diameter of the sphere increases as principal level increases. So if you take a look in the bottom of page 117, so go ahead and pause the video if you need to. 117, we see the difference between the s orbital in the first energy level. So it says that n equals 1. So that's the 1s sublevel, or the orbital in the 1s sublevel. And then we have the s orbital in the second energy level. Notice that it is larger. So as the energy level increases, the electrons are found further and further from the nucleus. So in the case of the s orbitals, their size just increases with increased energy level number. Next up, we have the p orbitals. If you go back to page 121 at the top of the page, we see some p orbitals. So how we describe the shape of p orbitals is that they are dumbbell shaped, or figure 8, whatever you want to call them. Remember, these are three-dimensional, so be thinking about 3 dimensions, not just 2D. Now notice, how many are there? Well, let me walk you through this way. How many electrons maximum can fit in any p sublevel? Pause the video, answer that question for me. How many electrons can fit in a p sublevel? Next question, how many electrons maximum can fit in any one orbital? Again, pause the video to answer that. So any p sublevel, whether it's a 2p, 3p, 4p, or whatever, can hold a maximum of 6 electrons. Now, if each orbital can hold only 2 electrons maximum, how many different p orbitals are there in the p sublevel? 6 electrons maximum, 2 electrons per orbital. That makes 3 orbitals. So the p sublevel consists of 3 different p orbitals, all 90 degrees apart from each other. They lie along the x, y, and z axes. So if you put all of those together, at the top of page 121, put them all together perpendicular to each other along the x, y, and z axes, that's what the 3 p orbitals, in this case in the 2p sublevel, would look like. So very, very important. Before I go to the next slide, we're going to talk about d orbitals. How many electrons maximum can fit in any d sublevel? D sublevel. Pause the video. Recall that the d sublevel can hold a maximum of 10 electrons. Well, if each orbital can hold just 2 electrons, how many different d orbitals do you think there are? So if we look at the bottom of page 121, we see the d orbitals. For most of them, except for that second one from the left, we call them X-shaped or flower or whatever you want to call that. So as long as you know kind of in general the shape of those orbitals, they're different than p orbitals. This time we have, as we can see at the bottom, 5 d orbitals. So every d sublevel is made up of 5 different d orbitals, each one that can hold a maximum of 2 electrons. Now, I mentioned before there's another sublevel, the f sublevel. We're not going to talk about that here, but just an extension of this. How many electrons maximum can fit in an f sublevel? That would be 14. So knowing that, how many different f orbitals are there in an f sublevel? That would be 7. So let's take a look again at another way of showing where the electrons are located in an atom. I say another way because one way we've already learned is through something called an electron configuration. Remember, in an electron configuration, we use numbers and letters. The big numbers, the coefficients, represent the energy level where the electrons are located. The letters tell us which sublevel, and then those superscripts, those other numbers, tell us how many electrons are in each of these sublevels. We'll take it a step further. Still showing the same things, energy level where the electrons are located, sublevel, this time also the particular orbital that the electrons are located in. So let's take a look at the symbols that we use in what's called an orbital diagram. There's a couple different ways. We'll start off with an empty orbital, an orbital that has no electrons in it. First of all, the symbols that we use, we represent orbitals with a line or a box or even a circle. And then the electrons are represented with arrows, usually, except for their circle notation. So an empty orbital, just a line, nothing above it, or a box with nothing in it. Half-filled orbital, remember any orbital can hold just 1 electron, so a half-filled orbital will have 1 electron in it. I like to draw my arrows like that instead of a 2-headed arrow. That's fine. If you want to do 2-headed, remember we're going to be drawing lots of these. Think about barium. Barium has 56 electrons. I don't want to draw my arrows, 56 of them, with double heads, so I'm going to draw them like this, just single-headed arrow, which is fine. And your book uses these similar, actually no, they use the double-headed arrows. I'm not going to use that. So an arrow above the line represents 1 electron in that orbital. Or an arrow inside the box. Or diagonal line in a circle like that. So I'm going to use the lines primarily. Just want to point out to your book, uses a little combination of the circle and the square. And then a full orbital contains 2 electrons, looks like this. So either one of those is fine. Again, I'm going to be using the one to the far left. Notice that I've drawn the arrows pointing in opposite directions. I'll explain why in a little bit. So those are the symbols that we use in orbital diagrams. All right, a couple things to think about before we get into some examples of drawing orbital diagrams. First of all, Hund's rule, before 2 electrons can be placed in any orbital, all the orbitals of that sublevel must contain at least 1 electron. Let me state this another way. Electrons prefer to be alone rather than paired if there is space available in the sublevel. Remember, electrons are negatively charged and electrons repel each other. So the electrons in a sublevel would prefer to be in their own orbital rather than paired up if there's room for that to occur. If not, then of course we need to pair them up. And we'll see what I'm talking about when we do some examples. Next, all electrons in half-filled orbitals spin in the same direction. So the direction that you draw the arrow indicates the relative direction that the electrons are spinning. So any electrons in half-filled orbitals in a particular sublevel must spin in the same direction. Let's add a 2.5 there too maybe, and we already saw this. Electrons in full orbitals must spin in the opposite direction. So that's why it showed in that full orbital notation that we have one arrow pointing up, one arrow pointing down to indicate that the electrons in that orbital are spinning in opposite directions. All right, let's take a look at some examples. Now, you don't really need to draw an orbital diagram from an electron configuration, but I'm going to show you the relationship. So we'll start off pretty simple. So hydrogen's electron configuration is 1s1. Let's draw its orbital diagram. So we start off with 1s, the S and S sublevel in the first energy level. Well, here's a question. How many different s orbitals are there in the 1s sublevel? Every s sublevel consists of just one s orbital. So how many lines are we going to draw? Just one. And for orbital diagrams, we're going to put the name of the sublevel under the line. So this line represents the orbital in the 1s sublevel. Next, we need to indicate how many electrons there are in this orbital. And for hydrogen, it has just one electron in the 1s orbital it has in the 1s sublevel. So orbital diagram for hydrogen looks like that. How about helium? Helium's electron configuration is 1s2. So let's draw the orbital diagram for helium. Let's start with the 1s sublevel. How many orbitals are there in the 1s sublevel? That would be 1. How many electrons does helium have in its 1s sublevel? It has 2. So let's draw those. Again, we have 2 electrons in the same orbital. They must spin in opposite directions. They do spin in opposite directions is probably a better statement. Therefore, to show that, we're going to draw our arrows pointing in opposite directions. Let's try one more like this, and I'll give you some to do without looking at the electron configuration. All right, let's start with the 1s sublevel. How many s orbitals are there in the 1s sublevel? That would be 1. So what I like to do is I like to set up all of my sublevels and then I'll add electrons. Or either way, you can go one sublevel at a time. Let's do that maybe this time. So let's set up the 1s sublevel. In lithium, how many electrons does it have in the 1s sublevel? That would be 2. Next, let's take a look at the 2s sublevel. How many s orbitals are there in the 2s sublevel? Again, that is only 1. Every s sublevel, the 1s, the 2s, the 3s, the 4s, the 5s, the 6s, and it keeps going, consists of only one s orbital. Now here's the thing. Be sure to draw a little bit of a gap between the lines for your sublevel. So I don't want to put the line for the orbital in the 2s sublevel right next to the 1s. So I'm going to put a little space there. How many electrons does lithium have in its 2s sublevel? 1 electron. Let's show that. You can draw that either pointing up or down. I always start with my arrows pointing up, but if you want to draw it pointing down, that's fine. And there we have it. All right, let's take a look at some more examples. I'm going to do quite a few more, so if you need more space, go ahead and use the margins or do these on a separate sheet of paper. I prefer them to be in your note packet so they're easily accessible and you don't have any loose papers with extra stuff on them. So let's take a look at carbon. First of all, how many electrons does carbon have? It has 6 electrons. Now go to the periodic table and think about the electron configuration for carbon. Now that you have that in mind, let's go ahead and draw the orbital diagram. We always start with the 1s. How many orbitals in the 1s sublevel? That would be 1. Carbon has 2 electrons in its 1s sublevel. What's the next sublevel to fill with electrons? That would be the 2s. So let's draw that. Again, carbon has 2 electrons in its 2s sublevel. Next sublevel to fill is the 2p. Here's where it gets a little different this time than the other examples we've done. Question, how many p orbitals are there in a p sublevel? Remember, the p sublevel can hold a maximum of 6 electrons. Any one orbital can hold 2 electrons. And so that means every p sublevel consists of 3 p orbitals, and we need to draw all of them. So I'm going to put a gap between the 2s and 2p, but a smaller gap between the lines representing the orbitals in the 2p. Here's what I mean. So I'm going to keep those together and show that they're separate from the orbital in the 2s sublevel. Now you have a choice here. You can label each line 2p, 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 or 2px, 2py, 2pz. What I like to do is just put the name of the sublevel under the middle line. Now looking at the periodic table, how many electrons does carbon have in its 2p sublevel? It has 2. So let's add those to our orbital diagram. Except this is not correct. Think about what we said with Hund's rule. Electrons prefer to be alone rather than paired if there is space available for that in the sublevel. So is there room in the sublevel for those 2 electrons to be each in their own orbital? Yes, there is, and so we're going to do that. That is also incorrect. Electrons in half-filled orbitals in the same sublevel spin in the same direction. What do you think? Does that look better? That's how we show it. Now, a common question is this. We have this empty p orbital. Do we have to show it in the orbital diagram? The answer is yes. Because you may have a question on a test that it looks like this. How many empty orbitals are in carbon? Or how many half-filled orbitals are there in carbon? The best way to answer that question is by looking at a correctly drawn orbital diagram such as this. All right, you want to try another? Let's go with oxygen. So go ahead, I'm just going to modify this one a little bit, but you go ahead and redraw oxygen. We have 1s2, 2s2. How many electrons does oxygen have in its 2p sublevel? It has 4. So let's fill up the orbitals in the 2p sublevel. Here's how it works. Add 1 electron to each orbital and then start pairing them up if you need to. So we have 4 electrons to place. 1, 2, 3. And then we have 1 more, which we can put in any one of those orbitals. Always go left to right. So let's put the 4th 2p electron in the orbital to the left. Spinning in the opposite direction of the first one that we placed in there. All right, want to try a harder one? Go ahead and draw the orbital diagram for iron. If you need to, write out the electron configuration first. I prefer you not to, but you can if you want. And then draw the orbital diagram. Pause the video and we'll compare when you're done. Hopefully you have something like this. So we have 1s2, 2s2. Next sublevel is 2p, fill it up completely. Next 3s, fill it up. Next 3p, fill it up. Next 4s, fill it up. Next 3d, so we have 5 different d orbitals. Sorry, I had to kind of squeeze them in there. And 6 electrons for iron total in the 3d sublevel. So I put 1 in each of these orbitals first, and then I added a second electron to the first orbital. So that would be the orbital diagram for iron. Want to try a harder one? Go ahead and draw the orbital diagram for the sulfide ion, it's called. So S-2 is called sulfide. It's the iron, it's the ion that forms from sulfur. Think about the structure. We've talked about this before. Think about the structure of this ion and draw its orbital diagram. Go ahead and pause the video. How many electrons does sulfide have? Well, sulfur, the neutral atom, has 16. That ion that has a -2 charge tells us it has 2 more electrons than protons. So that would be 18 electrons, just like argon. What do you notice? All of the orbitals are completely filled up. This is a stable arrangement of electrons, just like what argon by itself has, or in this case, this ion. All right, let's try a couple more. Now be careful with this one. If you're writing in pen, I suggest that you use pencil because this is probably going to be different than what you expect. So there are some atoms whose orbital diagrams, electron configurations are different than what you expect. There's some exceptions to Hund's rule, for example. And so I want to show you. There's a couple that you need to know. Chromium is one of them. The other is copper. There are others, but those are the only 2 you need to know. So go ahead and draw the orbital diagram for chromium in pencil, and then I'll talk to you about what it really looks like. All right, so here's what we would expect for chromium. Of course, we always fill up lower energy sublevels before we add electrons to higher energy sublevels. So, for example, we're always going to fill up the 4s before adding electrons to the 3d. Now, here's the thing. This is not the most stable arrangement of electrons in chromium. Now, if you take a look on page 120 in your textbook, you'll see that the 3d sublevel is really close in energy to the 4s. So here's what happens. This happens often, and again, you only have to know it for chromium and copper. But one of the electrons from the 4s sublevel actually moves to the 3d sublevel. And we end up with something like that. So chromium has a more stable arrangement of electrons if all of its 3d orbitals are half filled. So again, an electron moves from the 4s to the 3d, giving a full, half-filled 3d sublevel. Those words didn't seem to make sense to me when I just said them. So each orbital in the 3d sublevel is half filled, no empty orbitals. All right, let's see if you can predict what copper's orbital diagram looks like. It's similar to chromium's, but copper has a lot more electrons. So go ahead and pause the video and draw the orbital diagram for copper. So we would expect that copper would be 4s2 3d9, just looking at the last couple sublevels. 4s2 3d9. Well, similar to chromium, one of the electrons in the 4s sublevel goes to the 3d sublevel to give the 3d sublevel all filled orbitals. So that'd be 4s1 3d10. So again, there are other exceptions like this, but these are the only 2 that you have to know, chromium and copper. Next section is on Lewis structures, also known as electron dot structures. They consist of the symbol of the elements, comes from the periodic table, and then dots surrounding the symbol of the elements. The number of these dots corresponds to the number of valence electrons. Remember, valence electrons are those electrons in the highest energy level. Because of this, we usually only write Lewis structures for elements in which the last electron placed on them is in an S or P sublevel. So only for the S block elements and the P block elements. We can draw Lewis structures or write Lewis structures for either neutral atoms or ions. So let's take a look at a few examples. Here's how it works. Draw the symbol or write the symbol for the elements. And then what we're going to do is we're going to put an imaginary square around that symbol, and then the dots are going to go on the sides of that square. So how many valence electrons does sodium have? Let me ask you this first. What is the highest occupied energy level in sodium? Well, we can go to the periodic table. We see that sodium is in the third period, which means that its valence electron is in the third energy level. How many electrons does sodium have in that third energy level? Just one. So we can put a dot either to the left, to the right, on top of, or below the symbol. I'm going to put it to the right. Calcium, highest occupied energy level, fourth energy level. How many electrons does calcium have in its fourth energy level? It has two. So kind of like what we did with the arrows and orbital diagrams, we'll put one dot on each side of the imaginary square before we pair them up. So with calcium, I'm going to put them here and here. All right, let me give you a few more examples to work on. Go ahead and pause the video. Draw Lewis structures for aluminum, nitrogen, and bromine. Pause now, please. All right, aluminum has 3 valence electrons, so we want to put 3 dots around the symbol. Yours doesn't have to look exactly like that as long as you have 3 dots. Nitrogen has 5 valence electrons. Watch how I do that. Bromine has 7 valence electrons. All right, let's take a look at some ions. Let's start with sodium. So sodium, the neutral atom, has 1 valence electron. When sodium ionizes, it does so by losing its 1 valence electron. So if we started with this, for the neutral atom, we're going to just take off that electron. Now, how do we know that this is an ion? Anytime you draw a Lewis structure for an ion, make sure to put that symbol in brackets. And because it's an ion, we want to include its charge. The charge will go outside of the brackets. Go ahead and draw the Lewis structure for the calcium ion, nitrogen, and bromine. Actually, just do calcium first. Pause the video. I want to go over nitrogen together. Pause now, do calcium. When calcium forms an ion, it does so by losing its 2 valence electrons. So take those off, put it in brackets, charge outside. There's calcium ion's Lewis structure. Nitrogen has 5 valence electrons. Nitrogen wants to have 8 valence electrons. It wants to be like neon. So when nitrogen ionizes, it does so by gaining 3 electrons. Now I'm just going to show the electrons that the neutral atom gains in a different color to emphasize that this is an ion. 1, 2, 3. So 5 electrons that I have by itself, 3 more that it gains. And again, last step, we want to take that whole symbol and put it in brackets. And then put the charge outside of the brackets. In the case of nitrogen, it gained 3 electrons to form an ion with a -3 charge. Go ahead and pause the video. Draw a Lewis structure for the ion that forms from bromine. Bromine likes to gain 1 electron to form an ion with a -1 charge. There is the Lewis structure for the bromide ion. All right, next time we'll continue with excited states configurations. Thank you for watching.